Welcome. In this video, we will explore how to determine the specific heat capacity of a metal using the method of mixtures. Let's get started. So first of all, the metal is weighed and then placed in a beaker of water, and the water is heated to boil. So we are going to place the metal whose specific heat capacity is to be determined on this electronic balance and record the mass. We on the electronic balance and place the metal on it. We have 50 grams, but we change it to kilograms, and we have 0.050 kilograms. And let the mass of the solid be ms, and the mass of the solid is 0.050 kilograms. So we record it. We tie the metal to a string and put it in a beaker of water or any container of water that can be heated to boil, and we start heating it. While the heating is going on, we weigh an empty calorimeter and its stirrer. Let the mass of the calorimeter be mc, and we have 0.060 kilograms. So we record the mass of the calorimeter. And we are going to fill the calorimeter with water to about 3/4 of its volume and reweigh the calorimeter and water. Okay, so let the mass of calorimeter and water be mcw, and we have 0.164 kilograms. Now, to find the mass of water, we are going to subtract the mass of the empty calorimeter from the mass of calorimeter and water. So the mass of water is going to be 0.164 minus 0.060 kilogram, which gives 0.104 kilogram. And also let the mass of water be mw. So we are going to record the mass of water. That is, mass of water is equal to 0.104 kilograms. So we are going to lag the calorimeter by putting it into this insulation jacket to minimize exchange of heat with the external environment. And also, we are going to put a thermometer into this hole and record the temperature of the water in the calorimeter. So let the initial temperature of water in the calorimeter be theta I, meaning initial temperature of the water. And we have 31.7 degrees Celsius. So we record the initial temperature of the water. When the metal has remained in the boiling water for some time, the temperature of the solid which is the same as the temperature of the boiling water, is taken. Let the temperature of the solid be theta S, and the temperature of the solid is 99.1 degrees Celsius, so we record it. The metal is quickly transferred into the water in the calorimeter. The water is stirred steadily and the final steady temperature is recorded. So the metal is going to lose heat and the water in calorimeter will gain that heat. So the temperature goes up. Let the final steady temperature be theta F. As we can see, the final steady temperature is 34.2 degrees Celsius. And now let the specific heat capacity of water be Cw, and it's a constant. Specific heat capacity of water is 4,200 joule per kilogram per Kelvin. And also let the specific heat capacity of the calorimeter be Cc. And the specific heat capacity of the calorimeter is also a constant and is 400 joule per kilogram per Kelvin. It's a copper calorimeter. Assuming no heat was lost to the surrounding, the heat lost by the solid in cooling from the temperature of the solid to the final temperature is equal to heat gained by water and calorimeter in warming from the initial temperature of the water to the final temperature of the water. And the heat lost by the solid in cooling from the temperature of the solid to the final steady temperature is given by the mass of the solid, specific heat capacity of the solid, and the temperature difference between the temperature of the solid and the final temperature. Heat gained by water is also given by mass of water, specific heat capacity of water, and the temperature difference between the initial temperature of the water and the final steady temperature of the water. That is the final temperature minus the initial temperature. And the heat gained by the calorimeter is also given by the mass of calorimeter times specific heat capacity of calorimeter times the final temperature of water minus the initial temperature of the water. And we know the mass of the solid to be 0.050. Specific heat capacity of solid is what we are looking for, and we know the temperature of the solid and the final temperature, so we fix them. So we have 0.05 times specific heat capacity of solid, which we are looking for, times the temperature of the solid is 99.1 degrees Celsius minus the final temperature of the water, which is 34.2 degrees Celsius. And here too we have mass of water to be 0.104 kilograms times specific heat capacity of water is 4,200 joules per kilogram per Kelvin, and the final temperature of the water is 34.2 degrees Celsius minus the initial temperature of the water, which is 31.7 degrees Celsius. And for the calorimeter, the mass of the calorimeter is 0.06 times the specific heat capacity of calorimeter, which is 400 joule per kilogram per Kelvin, times the temperature change. And here 99.1 minus 34.2 will give us 64.9. And here 34.2 minus 31.7 will also give us 2.5. And 34.2 minus 31.7 will also give us 2.5. And here we multiply 0.05 by 64.9, which gives 3.245 times the specific heat capacity of the solid. And 0.104 times 4,200 times 2.5 will give us 1092 plus 0.06 times 400 times 2.5 is 60. So 1092 plus 60 will give us 1152. And we divide through by 3.245. So the specific heat capacity of the solid will be 1152 divided by 3.245, which gives 355.01 joule per kilogram per Kelvin. And this is the specific heat capacity of the solid used for the experiment. And now some precautions to ensure accurate results. The hot metal should be quickly transferred to prevent heat loss. And 2, the calorimeter should be well lagged. And also the metal ball should be quickly shaken to remove drops of water on it. And the mixture must be stirred gently and steadily to avoid splashing of water. And also when dropping the metal into the water, care must be taken to avoid splashing of water. These are some of the precautions taken to ensure accurate results. And now let's solve this example. A 300-gram iron, meaning the mass of the solid is 300 grams, and we convert it to kilogram by dividing by 1000. So that is the mass of the solid. Shot at 95 degrees Celsius, that is the temperature of the solid. So theta S, representing the temperature of the solid, is 95 degrees Celsius. Is quickly transferred into a lagged copper can, that is the calorimeter, with a stirrer of total heat capacity of 60 joule per Kelvin. So that is the heat capacity of the calorimeter, not the specific heat capacity. It means the mass is not needed. The mass of the calorimeter is not needed in this experiment. That is why we have the unit to be joule per Kelvin and the kilogram did not appear. So we are not going to use the mass of the calorimeter in our calculation, so we don't need it. Containing 500 grams of water, that is the mass of the water. We convert it to kilograms by dividing by 1000. Of water at 28 degrees Celsius. That is the initial temperature of the water. Theta initial, 28 degrees Celsius. Calculate the final temperature of the mixture. That is the theta final. The final temperature of the water is unknown. If the specific heat capacity of iron is 460 joule per kilogram per Kelvin and the specific heat capacity of water is 4200 joule per kilogram per Kelvin. So this is the question. Assuming no heat was lost to the surrounding, then the heat lost by the solid in cooling from the temperature of the solid to the final temperature is equal to heat gained by water in calorimeter in warming from the initial temperature to the final temperature. And heat lost by the solid is given by the mass of solid, specific heat capacity of the solid, and the temperature change. That is from the temperature of the solid to the final temperature. We find the difference by subtracting the smaller temperature from the bigger temperature. And heat gained by water is mass of water, specific heat capacity of water, and we subtract the initial temperature of the water from the final temperature. And for the calorimeter, remember we don't need the mass. So we have heat capacity of calorimeter times the temperature change of the calorimeter, which is the same as that of the temperature change of the water. So we fix the values. We have the mass of the solid to be 0.3 times specific heat capacity of the solid was also given to be 460 joule per kilogram per Kelvin, and the temperature of the solid was 95, but we don't know the final temperature. And for the water, the mass is 0.5. The specific heat capacity is also known. The initial temperature is known, by the final temperature is still unknown. And for the calorimeter, the heat capacity is 60. We don't know the final temperature of the mixture, but we know the initial temperature. So here 0.3 times 460 is 138, and 0.5 times 4200 is 2100, and here we have 60 multiplying the final temperature minus 28. So we expand brackets. 138 times 95 is 13110 minus 138 times the final temperature. And here we have 2100 times the final temperature over here minus 2100 times 28 giving 58800. And here we have 60 times final temperature minus 60 times 28 is 1680. So we group like terms. We group all variables containing final temperature to this side and the other numbers to this side. So we have 13110 plus 58800. Since it's negative, when it crosses the equal to sign, it becomes positive. And 1680 is also negative. When it crosses the equal to sign, it becomes positive. And we already have 2100 final theta here, plus this 138 theta f crosses the equal to sign to become positive, and we also have 60 theta f here. We add all these numbers and we have 73590, and here 2100 plus 138 plus 60 will also give us 2298 theta F. So we divide through by 2298. And 73590 divided by 2298 is 32.02 degrees Celsius. And this is the final temperature of the mixture.